get started. Any questions on the gas laws? No? All right. We started talking about the kinetic molecular theory a while back, around the time we started the gases. But let's get into that a little bit more. So if you remember, yeah. Oh, thank you.
Is this still 7.17 or is this 18?
This one's 718, and we'll hopefully do 818, 819 today. So if you remember, kinetic molecular theory just tells us how gases behave why gases behave the way they do. So let's, one of them we talked about was, as the temperature of a gas increases, what happens? Kinetic energy, right? Kinetic energy also increases. They're directly related. So if you remember, maybe we didn't talk about this, but so does every gas molecule have the same speed at the same temperature? What do you think? Some are moving slower, some are moving faster. So we said that the average kinetic energy is proportional to the temperature, yeah? So first thing we're going to do is determine how to calculate this average speed. Not the average kinetic energy, but once we know the speed, kinetic energy is just 1/2 mv squared. Okay? We're probably not going to worry about that too much right now. So the average speed is called the root mean square velocity. And if you're not sure, velocity is just a speed with a direction, right? So when we say velocity, we mean speed, but we're talking about a vector quantity, but anyway, that's more physics. We'll just keep it simple-ish. So the equation for root mean squared, so the average velocity, or the root mean squared velocity, is equal to the square root of 3RT divided by this symbol that looks kind of like a micro, but it's not. If you look on your reference sheet that you get for the exam, I have a hard time drawing it just like that, but it's kind of like a squirrely M that does this or whatever. Something kind of like that, but that's hard to draw. So I'm just going to draw it like that. Is that okay? All right, so this M looking thing, that's the molar mass. That's all it is. So do y'all remember what R is? It is a constant. What's the value? 0.0821. That's only if we're dealing with, ATM liters per mole Kelvin, right? But if we're dealing with molar masses and we're dealing with speed, how do we get speed out of this? Out of ATM and liters. That doesn't make any sense, does it? Okay. So we got to use a different value, and just so this is going to be 8.314 joules per mole Kelvin. So a little bit different unit. Now let's try to make sense of this. Joules, and we'll talk a little bit about this next section, which hopefully after break we'll see. We're a little bit behind, but anyway, so joules is the unit for energy, and to calculate that it's just force times distance, or Newton meters. And a Newton is the unit of force, and that's just a dude's name, Newton. So if you ever taken physics, it's mass times acceleration. So mass, kilograms times meters per second squared. So that's the unit for force. And then we multiply this meters, so it's going to be kilogram meter squared per second squared. Guys, I'm just trying to derive something here. So don't get hung up on, oh, what is he even talking about? Because it looks a little bit scary, yeah? All right, so velocity is measured in meters per second. Y'all good with that? Distance over time, okay? So if we have the square root of, now this 3 is just a constant number. That doesn't have any units. And R is going to be joules over mole Kelvin, times the temperature better be in Kelvin, divided by molar mass, which is grams per mole. You with me? Now, if we plug this into our joules, we get kilogram meter squared per second squared. What cancels out here? Got Kelvin canceling out, moles canceling out. Anything else? Not quite. So this M right here, that's the molar mass measured in kilograms per mole. So it's another conversion to convert that to kilograms. So if we do that, that's a kilogram there, and the kilogram cancels out, leaving us with the square root of meters squared per second squared, which is meters per second. You follow? So that's going to be the average speed of our gas at a given temperature. You with me? Do you have to know all this stuff, guys? Not yet. Wait. No, you won't. You will not, okay? So this right here, you have to know how to use that formula. And we kind of have a lot of formulas in this class, is that right? But most of them are on your reference sheet that I give you. And so basically you just have to know how to use it. And if you guys get good at the problem solving strategy, it'll tell you what you got to use. You might have to look at your reference sheet to find it if you're not familiar with it. But better just become familiar with it, right? Any questions so far? All right, so just let's look at some relationships here. Our root mean squared is the square root of 3RT over the molar mass in kilogram per mole. And we can see that the relationship between the average velocity is not equal to, proportional to square root of temperature, right? The speed is related to the temperature. Well, if you look at the equation, kinetic energy equals 1/2 mv squared. If you square root both sides, then, and this is also related to the temperature, right? Directly related to the temperature. So we can kind of, it's not exactly T, but that's kind of how I get that relationship. So as the temperature increases, we know the speed increases. But we kind of intuitively already know that, yeah? Maybe, maybe not, yeah.
What symbol are you using for root mean square? Is that a V?
Yeah, V for velocity.
Okay.
And it,
With the-
so this V right here is for volume,
Mhm.
and a V, kind of like a cursive V, that's velocity. And if you've ever taken physics, then that's, well, sometimes they use U, but we won't go there.
What's
Okay.
in the blue? Is it KTE?
Sorry, that is basically the temperature.
Oh,
So kinetic energy we learned a while back is proportional to the temperature, right? So that, therefore, the temperature, the velocity is proportional to the square root of the temperature.
gotcha.
Does that make sense?
Yeah.
And basically what this tells us is as we increase the temperature, the speed goes up too. Good? So why am I showing you all these relationships? Yeah.
And the square root next to t, is that 1/2? What's the thing next to it?
Right here?
Yes.
1/2 mv squared. That's just the equation for kinetic energy. In this class, I'm not going to have you calculate kinetic energy, okay? But that's how you do it. Good? So the reason you need to become familiar with the relationships, that way you don't have to do a lot of calculations just to make a prediction. Okay, we double the whatever, we know what's going to happen to this, right? So if you can understand relationships, that really helps us not have to do a lot of math and make a pretty good guess or estimate, okay? And another one that's important to know is the root mean squared is proportional to, if we look at this, 1 over the square root of the molar mass. So what does that tell us? As the molar mass of our gas increases, so if we have a substance that has a greater molar mass, what happens to the speed? It what? It decreases. We divide by a bigger number, the velocity or the speed becomes smaller. Does that make sense to everybody? And so if we know that, then we can answer some simple questions like, which molecule will tend to go faster at a certain temperature, right? So if the temperature stays the same for each molecule, then we got to look at the mass. Make sense? So for example, if we have helium and hydrogen gas, which one's going to go faster typically? Yeah, hydrogen because has a smaller mass, right? Smaller molar mass means it's going to go faster. Does that make sense in your mind? Questions on that? Do you have a question? No? Okay. So we could just say smaller molar mass means faster speed or greater speed.
Maybe a dumb question, but if would it have to be the mass of H2, or is it just the mass of a single hydrogen versus the mass of a single helium?
Just the molar mass. So this right here is the molar mass.
So you don't have to like multiply by 2.
So we don't have to know how much we have. We're just saying, we're talking about This root mean squared is the average speed per molecule, right? The average molecular speed. Yep. So if we have just a lump sum of hydrogen gas, that whole thing's not moving. It's just each molecule. Great question. That's not a silly question. Any other questions on this before we move on? For example? All right. So we did one example right there. So you should be able to do that pretty quickly without doing hardly any math, right? Especially if it's like carbon dioxide and oxygen gas. We can see which one's going faster. Oxygen because, well, less molar mass, right? They both have O2 in it. The other one has an extra carbon, extra 12 grams per mole, okay? Does that tell us how fast it's going? No, it just tells us which is moving faster. Good? All right, so let's do an example here using the root mean square. And you're going to have to be able to do this on the exam. This equation is on your reference sheet, so if you forget it, well, you just look at it, right? So here's an example. We have argon gas at 400 Kelvin has a root mean square of what? So we do have to know what the temperature is before we can do this. So our equation is root mean squared equals square root of 3RT over molar mass. Remember that molar mass has to be measured in what? Kilograms per mole. Otherwise, the units won't cancel, and then it's just a nonsense number. Okay? So that's really the big thing that you have to remember. This is in kilograms per mole. So once we find grams per mole, just convert grams to kilograms. And we can all do that, yeah? Okay? All right, so let's plug it in. This is equal to square root of 3 times R. What's the value of R if we're trying to find speed? 8.314. And is that one on our reference sheet? I believe it is. Let's see. Yes, it is on your sheet. Both R values are on your sheet, and they're both called R. They just have a different unit. If we have different units besides the ones we're dealing with, it's just going to be a different number. But these are the only two values that we need to use in this class. So 3 times 8.314. And if we put our units in just to make sure they cancel, and it's a good idea to include units. Then you won't accidentally put grams per mole in there, right? And that'll help you to catch the mistake if you make it. So joules per mole Kelvin times the temperature is 400 Kelvin divided by the molar mass of argon. Look at our periodic table and somebody tell me what it is. 40 something? 39.95. So 39.95 grams per 1 mole. So we got to convert grams into kilograms by dividing 1,000 to it. So we got to do a conversion before we stick it in there, right? So that's going to be 0.03995 kilograms per mole. Did I do my math right? 1, 2, 3, yeah. And then just to make sure all of the units cancel appropriately so that we know we're not missing anything. Except for that one, it doesn't really work unless you know what that is, right? If you want to just know if you have kilograms, it'll cancel out and you'll have meters squared per second squared. Then you square root that and it's going to be meters per second. Or you can know that joule is a kilogram meters squared per second squared. Your call. Okay? All right, we do that and we get our root mean squared is 499 meters per second. So on average, argon gas at 400 Kelvin is going 499 meters per second. That means some are going faster, some are going slower, but on average, that's what it is. Questions on that? Yeah, make sure you guys can calculate this because there's a square root, makes you follow order of operation, right? Do all of the math and then square root the answer. Good? There's a lot more examples for you here. Does anybody need another one before we move on? Okay. So let's, I would practice that. The answers are on Canvas on the home page. You guys know where to find these worksheets and answers? Okay. Anybody not? All right. Okay, the next thing we want to talk about is diffusion of gas. And what this is gases will move from one concentration to another, they'll move from a higher concentration to a lower concentration. You guys understand concentration? We did that before, yeah? Okay. So, for example, and we kind of talked about this a little bit, but and at my high school, you see this all the time. Young teenage girls were going there all over, right? Saying, oh my gosh. High concentration right here around this young teenage girl, and then it spreads throughout the whole class until everything's in equilibrium. And then if you can still smell it, that means they just use way too much, right? But it'll diffuse until it's kind of the same everywhere, the same concentration of that gas everywhere. Make sense? Okay. So let me just give you a definition here. This is the process by which gas molecules disperse in space in response to difference in concentration. So we can say in our own words, because that's a lot of words and a lot of, right? So if we say it in our own words, we say gases move from higher to lower concentrations until what?
Equilibrium.
Until equilibrium, until it's all the same concentration, right? Are we good with that? With that definition? So what does this depend on? Depends on a few things. Depends on concentration gradient we just talked about. So if there's a bigger difference, so when we say concentration gradient, if someone just sprays one little squirt of that perfume on them, it's not a huge difference, right? But if we have a whole bunch, then you got a huge difference, and then it's going to diffuse more quickly. Make sense? Might take longer to be all in equilibrium, or maybe equilibrium still smells bad, but anyway. So this is the bigger difference. Refers to faster diffusion rate. I should say up here, this is diffusion rate.
Wait, sorry, which is diffusion rate?
What?
Which is diffusion rate?
So this right here, we're talking about diffusion rate.
Gotcha.
Diffusion rate depends on these things here. So the rate at which it diffuses depends on your concentration gradient, meaning the difference in concentration. So it also depends on temperature. So if we have a high temperature, faster diffusion rate. Does that make sense to everybody? Things are moving faster if it's hotter, right? And size of molecule, we just talked about. Well, not with diffusion, but it's the same idea. The smaller the particle, faster or slower? Faster, right? It's going to have a greater root mean square velocity or speed, and so it's gonna diffuse faster. Smaller particles particles means faster. And when I say smaller, that's kind of related to the mass, right? Remember, the space of each molecule is negligible. But, so the mass kind of refers to the size as well.
So rather than specifying size, doesn't it make more sense to specify mass?
Sure. Okay, the area. Hold on. Okay, yeah. So the area, the space that the gas is in, and it's really the two-dimensional, it's not the volume, but the area. So like if we have a tube here and a bigger tube here, which one is gonna disperse faster? Larger one has more space, right? Okay. So this area right here versus here, larger area is a faster dispersion rate.
Why would it be faster and not just like more complete?
What do you mean by more complete?
Like,
It reaches equilibrium faster because there's more.
is that because there's like less pressure on there? Or like, why would the size of the container that it's in affect other?
Not the volume. So I'm not talking about the volume, but if you have, let's see.
Or I guess maybe that's what I'm asking, is like, how does volume affect it? And if it doesn't, then why does the area? Like, is that what I'm asking? And also maybe I'm asking.
No, great question. Yeah,
What is it like in equilibrium in regards to? Like,
concentration. So well, not just, well, you have, yeah, concentration. If you have your perfume's real high concentrated, it's gonna disperse into less concentrated areas until it's all the same concentration. Yeah.
Is the area, is that affected because like, if you had like a little bit in one spot, if you had like a bigger container compared to the rest of the container, that seems to be more concentrated comparison versus if you added that same amount in like a smaller container, is that how that works?
Yeah. And so you have a bigger space, you have more room for those gases to go, it seems like, right? But it's not just the volume, so that's kind of what I'm kind of not communicating correctly. So your area, there's more area for the gases to go into in that area. I mean, if it has a bigger area, it will have a bigger volume if it's longer, right? But it has more places to go. It can diffuse in a lot of spaces rather than just right here. Does that kind of make sense?
Oh, like it exponentially increases?
Yeah.
Yes.
It kind of just says, okay, you can go here, 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 rather than just here, 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 here,
That makes sense.
right?
Thank you.
Okay. No, thanks for asking. Sometimes those great questions make me think and help me to understand it better too. So great. Helps everybody. We good? And the last one is density or viscosity. You guys know what viscosity is? Like oil is more viscous than water, right? So we got a higher density or viscosity, then it's slower. Guess I should say, should I do them all the same? Be consistent the way that I'm doing this. So lower density or viscosity means this could be faster. This one right here, the size or the mass, that's the main one. Okay, I mean, you need to know it all, but because not just one, it doesn't depend on just one thing, but we good? All right, so the question I'll ask is, which gas has a greater diffusion rate? C3H8 or CO2. You guys doing this? My iPad's almost dead. Yeah. CO2 has a greater dispersion rate because it's heavier.
You got it flipped.
Smaller particles are faster. So yeah, you got it flipped. Right idea. So this, if we look at the molar mass, this is 44.01 grams per mole. And this one over here is what? 30, what is it?
It's 15.034.
Not quite.
Oh,
So there's
whoops,
three.
Yeah, there's 3 of them.
12.01 times 3
And then there's 8.
plus 1.008. I think these are pretty close to the same.
I think they're the exact same.
Did I pick bad one? That's okay. It's not a bad one. Do say, okay, they're the same. So what is it? 44 point what? 097? Oh, so basically the same, right? Therefore, this one's going to be a little bit faster. Not much, though, with negligible amount, right? All right, so we'll just say these are the same. I tried picking one that looks bigger and is smaller. I kind of did that, but so don't go by what it looks like. You have to actually calculate the molar mass. We good? All right, let's move to effusion rate. So dispersion is they're moving to make equilibrium. Effusion rate, or effusion, is to the escape of a gas through tiny holes. What's an example of this? A balloon, right? Eventually it's going to leave, so your helium balloons will eventually sink, right? Because now all the helium gas is leaving. But there are tiny, tiny holes in our balloon, because remember, most of an atom is empty space, right? But the thing that I was thinking of last weekend, we went camping, is a blow-up mattress. Like, these things always deflate while you're sleeping, right? Okay, so we got effusion is when the escape of a gas through tiny holes, through a tiny hole. So what does the effusion rate depend on?
Size of the hole.
Size of the hole, okay. What else? If we're talking about the same hole, what does it depend on?
All the other factors above.
Yeah, heat, right, all those things. But the biggest one is the mass, the size of it. So we actually have an equation here. So the rate of effusion I'm not going to write it like that because that looks like effective, right? Something else we've done. I'll just say the rate is equal to 1 divided by the square root of the molar mass. Now, does that have to be measured in kilograms per mole? What do you think? It does not, because there's nothing for it to cancel out with, right? And that's the only reason why we changed it to kilograms per mole, so to cancel out with kilograms and leaving us with meters per second. So here we're okay with just using molar mass.
So in our previous equation, it was only because of
Joules.
R, because of joules.
Because of R, yeah. Yep. So when you use that formula to find the root mean squared, yeah, we got to have kilograms per mole. So if we want to compare the rate of two gases, we could say the rate of one gas in relationship to the rate of another gas. That's going to equal the square root of the molar mass of gas B over the square root of molar mass of gas A. And we can rewrite this mathematically as the same thing. The square root of molar mass of B over molar mass of A.
Wait, that's square root of A and B, not R of A, right?
Yeah, so the rate of, let's say, hydrogen gas.
Oh, that is R.
So, yeah, the R's, yeah, that's the rate. Now, on the exam, I'll say, okay, this gas has twice the fusion rate as this other gas, of an unknown gas. Calculate the molar mass of an unknown gas, right? Question?
Your rates are A over B, but then in the square roots, it's B over A? Oh, yep, okay. Makes
No.
sense, actually.
Yeah, great. Always ask, always ask. We good? Let's do an example of what you might see on the exam. So helium has an diffusion rate about 3.08 times faster than an unknown gas. So we want to know, what's the molar mass of unknown gas? Who cares? Why? Because we can predict what the gas is. All right, so how do we go about this? If we're comparing two gases, we're going to use this equation right here. So we can call this equal to rate of, which one goes on top? Helium or the unknown gas? How do we know helium?
It's larger.
Because it's larger, and we know the rate is bigger than 1. Do we get that? More than 1 times faster. So that's going to be the rate of helium over the rate of the unknown gas. And what is the ratio? 3.08. Does that make sense to everybody? And the equation for that is the square root of, what goes on top?
The unknown?
The molar mass of the unknown gas, that's what we're looking for, over the square root of the molar mass of helium. Are we good there? So what is the molar mass of helium?
4.003?
4.003. And again, can we just leave that as grams per mole? We can if our answer wants to be in grams per mole. And if we want to know what gas it is, that's the best way anyway, because our periodic table tells us in grams per mole. So now we just do a little bit of algebra, or, right, calculate for X here, for molar mass of our unknown gas. So this is basically 2. Should we round it? Not if we want a better result, right? So we can multiply both sides by the square root of 4.003. And so now we have 3.08 times square root of 4.003 is equal to the square root of our molar mass of our unknown. How do we solve for the unknown? Square both sides. You with me? And so our molar mass of our unknown gas is equal to, and I might have rounded this in my calculation. What do you get?
I got 37.974.
37.974
Yeah.
grams per mole. I'm not going to ask you what gas you think it is, but you could probably figure it out maybe if you knew a lot of gases, right? Maybe if you had a list of gases to choose from, right? But if you didn't, you're scrambling.
It's like it's between chlorine and argon.
But remember, chlorine is Cl2, so this is close to argon. And so depending on the chemical formula, so you see that'd be kind of hard to tell without a list, yeah.
Following that equation at the top, we decided to put helium on top, right?
Yeah, do you understand why?
Yeah, but then when you go over, we put helium on bottom.
Because the equation for the fusion rate is 1 over the molar mass of our gas. So if you did, let me write this a little bit different way to make this clear. So the rate of helium is 1 over the square root of the molar mass of helium. And the rate of our unknown gas is 1 over the square root of the molar mass of our unknown gas. Follow? And if you did rate of helium divided by rate of unknown gas, then you got 1 over rate of helium divided by 1 over the square root of molar mass of helium over the square root of the unknown. You follow? And then you have division of fractions, you just flip and multiply. Great question. Does that make sense to everybody? Why our formula is this here? Or I should say this here. Okay? Yeah.
Do we put the larger gas on top because we can't get a decimal point for an atomic mass?
We put the larger gas on top because this number right here is greater than 1.
Okay.
If it says the rate of helium is half as the rate of the unknown gas, we put the unknown gas on top because a half is smaller than 1. Does that make sense? You have a bigger guy on top, divide a smaller number, you're going to get a number that's greater than or equal to 1, right?
Just a question, why didn't we equal that to 3.08? Why did we do our helium over our unknown equals 3.08?
Because the equation says the ratio of their rates, so the rate of helium gas compared to the rate of the unknown gas, the rate of helium is 3.08 to 1. 3.08 times greater. Does that make sense?
This one says faster, no? Is it the same thing?
Rate is speed is a rate, but we're not talking about meters per second. We're talking about how fast these molecules go out this little hole. So it's not a speed, it's a rate. Just like you have a rate that you get paid, right? It's not a speed, but it's still a rate. What makes it a rate? Per unit time, right? That's what makes it a rate. Good?
Scroll down to the example problem.
How are we feeling? Yeah, Michael. Go, good? we have questions in our mind or maybe uncertainties? All that tells us is we need to do some more. Should we try another one?
Yeah.
Okay. Okay, let's do on our 7.81 worksheet, section 4. Should we just do the first one? Or do you have a preference? Anybody else need one of these? There's some up here if you need one. So the effusion rate of an unknown gas is 2.83 times faster, or I should say greater, right? Because it's not a speed. Greater than the rate of oxygen gas. We want to know what is the molar mass of our unknown gas. So before we plug any numbers in, let's solve for what we're looking for, yeah? Or do you guys like to plug numbers in first, then solve? Okay. So the last one we plugged our numbers in kind of and then solved, right? Kind of did half and half. So the equation is rate of substance A over the rate of substance B is equal to the square root of molar mass of substance B over square root of molar mass of substance A. Good? All right, now we got to decide which one is A and which one is B. Which one goes on top? The unknown gas or oxygen gas? Unknown because it's larger. Okay? Does that make sense to everybody? Okay? So we'll say, okay, this is the rate of the unknown gas over the rate of oxygen gas is equal to the square root of the molar mass of oxygen gas over the square root of the molar mass of the unknown gas. Any questions on setting up the formula? Okay. And what are we looking for? The unknown gas. So how do we do this?
Set it equal to the rate that you know of.
We could. Do you want to solve symbolically first or? So we need this to be on top, don't we? So we multiply by the square of the molar mass of the unknown gas to both sides. Okay. Now we got to get rid of this stuff. We can flip and multiply, or we could just divide both sides by RU over RO2. You with me? So it's getting kind of messy there. So we got the rate of the unknown gas, square root, is equal to the rate of oxygen molar gas, square root. And then divide that by RU over RO2. This one might be easier to do halfsies, right? Kind of like we did it the first way. Should we do that? No? You can do it either way, you really can. But this kind of looks icky. And if we square both sides, that's gonna be what our molar mass is. Anybody freaking out with this? Looks a little messy. Should we try it a different way? Okay, let's do. But if you follow it, no problem, you can do it that way. It's okay. Okay, so I'm gonna come back here. Here's my original equation. RU over RO2 equals square root of molar mass of O2 over the square root of molar mass of unknown gas. All right, what do we know so far?
That equals
We know our rate is equal to what?
2.83.
2.83. Any questions on that part? Good? Okay. So now we have 2.83 equals square root of molar mass of oxygen. Should we just put it in there? What's the molar mass of oxygen gas? 32, good. Do we need to worry about units here? You do, as long as they're the same, we're okay, right? Over the square root of molar mass of the unknown gas. Okay, we still need the molar mass of the unknown gas on top, yeah.
So is it fair to say that like a version of this equation would be the change in rate is equal to?
Not
Is that
quite,
ever not true?
not quite. It's not the change in rate, but it's
Difference
it's
in rate.
not the difference either. That difference kind of sounds like change, right? Because it's the difference is minus. So it's really the ratio of rates. It really is. So if one is 2.83 times greater, then it's 2.83 to 1. Does that make sense? And we don't have to worry about the 1, so we just say it's 2.83. So now we can multiply both sides by the square root of the molar mass of our unknown gas. Woo! That was weird. And we want to get our unknown gas all by itself. So what do? Divide both sides by 2.83. Is our molar mass all alone yet?
Square.
Square it. If we square this side, we have to square this side. Do you see this looks just like the other one, just kind of with numbers instead of all the variables? So either way would have worked. So we get the molar mass of our unknown gas is equal to the square root of 32, divide 2.83, and then we square our answer. Make sure you do it in order of operation. Good? And what do we get? I don't have the answer right in front. Actually, 3.99 or close to 4. What? What are the units?
Grams per mole.
Grams per mole. So that's going to be what? What do you think that gas is?
Helium.
Oh, basically helium, right? Okay. How are we feeling? Clear as mud? And you got more there to practice? I would definitely do it. It's going to take practice to get to where you can do this on your own. I apologize, my answer key just has the answer, not the solutions. I've been doing these as we're going, because this is the first time I've taught this course. And so, yeah, I'm just doing what I can to keep up, but I barely had this printed out today. I finished it during my during this morning before my first class, and then, but anyway, I'm not trying to make excuses, I'm just saying. Okay, there's one more part to the kinetic molecular theory. Do you have any questions so far? So diffusion is when gas diffuses in space so that it reaches equilibrium. Effusion is when gas leaves a container through a small hole, right? And everything has holes in it. Everything as we know it, okay? Tiny, tiny holes. All right, we good? All right, this next one, there is one example just like what we're going to do next on the exam. And it's talking about non-ideal gas behavior. So are we good with the ideal gas behavior? So this problem is basically a test to your algebra. Sorry, I really am. But it is on the exam, so I'll show you how to do it. It's not hard, it's just a lot. Okay, here we go. Now I scared you. Now I'm going to show you. Say, oh, that's not too bad. Maybe. That's my plan. Okay. All right. So for non-ideal gas behavior, and it's not a whole lot different. Slightly different values. But if you're going to become a scientist and that wants to get close, you might need to use this, right? So anyway, here we go. Let's just do it. So we know PV equals nRT. And this R we use here is the 0.0821 value, right? ATM liters per mole Kelvin. And we're still going to use that. And so it turns into, our pressure is going to change slightly to correct the molecular attraction. Now we said gases don't really have the intermolecular forces because they're so far apart, right? Do they really? Well, they do, but it's small. Yeah? And so if we're just making a prediction, ideal gas is great. If we need to know really, really close and really dead point on, this is when we use this. Because when is things ideal? Never. Okay, so the ideal for conservation of energy is whatever you started with, that's what you get, right? Does it always work that way? It does really, but for our misconception, not misconception, for our lack of perfected, what is it? Being perfect, then we cannot get exact if we do this mathematically, okay? Maybe that wasn't a great example, but here it is. The pressure, so we're going to add some value A, and I'll tell you what this A is in a minute. It's just a number that you have to, and they have a whole table of these values for different gases. And so on the exam, I will give you A, and I will give you B. So you just have to plug it in and solve. That's it, okay? Just like I said, it just makes you do some math, basically, right? So this part right here corrects the molecular attraction for molecular attraction, or repulsion, either one. So that's the P. And then our V, a little bit nicer, volume minus NB. And I'll give you this A value and this B value. And so what is this correct for? We said the volume of a gas particle is what? Negligible, right? Is it 0? It's not 0. So it corrects for the volume of the molecule. Molecule, okay? And then that's going to equal, you're going to like this part, nRT. Woo! So PV equals nRT. So when we have high pressures and low temperatures, we could just go with the ideal gas. But if we have low pressures and high temperatures, we're going to have to deal with this one. Okay? So maybe I'll say that again. For high pressure and low temperature, then that's where we can just do the ideal gas law. So what tells us it's too low of pressure, too high of temperature, right? We don't have to worry about that. Okay? So let's do an example. Are we good with this? And this, I believe, is on, it better be on your reference sheet. Let's see, I think it is. Ooh. It is not. You better have this on your reference sheet. Did you guys write it down? I don't know why it's not. Unless I can't see it somewhere. No? Yeah, it's not there. Dang it. Everybody write this down? Yeah.
So this is the non-ideal gas law. This is for low pressure, high temp?
No, this is, so ideal gas law is for high pressure, low temp. So, oh yeah, low pressure and high temp, yeah. Yep.
You're saying the problems will specify to use ideal or non-ideal?
Well, yeah, it'll give you an A, if it gives you an A value and a B value, you better use the non-ideal. So it's really not that hard if you have this on your reference sheet. It'll be very difficult if you don't. Does everybody have this written down? Yeah? Question?
So is this essentially just telling us that PV equals nRT? Or
It does. This is our pressure, this is our volume, but it has a correction for molecular attraction at low pressures, because if they're low pressures, then they kind of have a little bit of an attraction.
okay, so
And it's, yeah.
sorry.
So what is the significance of A and B that you give them to us? Do you know, like?
The first and second letter of the alphabet. It's just no, I'm just kidding. It's just a constant. But why do we use A and B? Because it's the first and second letter of the alphabet. So it's just a constant to help us to account for that correction. And how we got this, I'm not even gonna go there. Okay, yeah,
Back to my previous question. So we're saying if it's non-ideal, that's how we'll solve for our P, that's how we'll solve for our V?
uh-huh,
Okay,
that's it.
that makes sense.
And how will you know it's not ideal? It,
Oh, sorry.
it'll give you an A value and a B value.
Yeah.
And there is one problem on the exam where you have to use this formula. Okay? All right. So let's do an example. So for chlorine gas, we want to determine the pressure of a non-ideal chlorine gas. We know the volume is 22.4 liters. The number of moles is 1.5 moles. And the temperature is 273.15 Kelvin. Who can tell me what this is saying? At STP. Do you guys see that? How do we know? So at STP, what should the pressure be? 1 atm. That's for an ideal gas. And now let's see what it is for a non-ideal gas. All right. Oh, let me tell you what this is called, because I think on the exam it tells you, use the van der Waals equation. That's what this is. You good?
Walls,
WAALS. So next unit, we'll talk about intermolecular forces. Those are the van der Waals forces. I don't know if you've heard of those. But anyway, that's what this is right here. Okay. All right, so let's do this. So the formula is P plus AN squared over volume squared times V minus BN equals nRT. Okay. Should we solve symbolically first? This one is going to be a little bit nicer. Okay. So this one will be easier to do that. Okay, we're solving for P. That's our question. What's the pressure?
We don't know A or B.
Oh yes, let me give that to you. A value is 6.49 and B value is 0.0562. Thank you.
What unit are those in? No unit?
No units. Well, there's probably a unit. Let's just not worry about it here. All right, after this problem, we'll take a break. Okay? Okay, so let's divide both sides by V minus BN, right? Are we okay with that step? Then that's gone, and we can get rid of those parentheses. How do we get P by itself? Minus AN squared over volume squared to both sides. And if you want to write this down, you can. Then it saves you a little bit of algebra, right? So our pressure is equal to nRT over V minus Bn minus AN squared over V squared. And our V is our volume, right? All right. So now we're going to just plug our values in. N is our number of moles, which is 1.5 moles. R is 0.0821 ATM liter per mole Kelvin. And temperature is 273.15 Kelvin, divided by our volume, 22.4 liters, minus our B, which is 0.056 times the number of moles, which is 1.5 moles. Minus A, which has a value of 6.49, multiplied N, which is number of moles, 1.5 moles. We've got to square that value over the volume, which is 22.4 liters, and we got to square that value. So just be careful when you do this problem. Double check, make sure you have it set up right. Follow order of operation. So maybe you can do one step at a time. You multiply those, you simplify. Multiply those, subtract it from this, then divide this, and you get an answer, right? Square this, square that, multiply and divide, and then subtract this value from this value. We all good with order of operation? Okay.
What units should we get?
Yeah, that's a great question. Should we see, this one's going to be hard to cancel units, right? Because this one doesn't have a unit, but maybe it's supposed to. This one and this one. So maybe just make sure you're in ATM, liters, moles, and Kelvin for everything else, and you should be good. I know that's not great, but what'd you get?
It should be ATM.
Yes, we should be in ATM. We're looking for pressure. If 1.06?
5.6.
1.48.
I got 1.48. Maybe I did it wrong.
That's what I got too.
1.48?
4.478.
Yeah, 4.48 ATM. That's because it's messy. What?
You rounded it to 3 sig figs, isn't it, too, because of 1.5 mil?
Yep, you're right. So 1.5 ATM. And just to tell you about sig figs, on this last one, I think I'm going to start making them without using sig figs, just because I had AI do this, and so if you did without sig figs, it'd be hard to tell if you did it right. Kind of. So, anyway. But on the test, on the exam and homework, yeah, use sig figs.
I was wrong.
Did you figure it out what you did? And it really is easy to make mistakes. When you do a big calculation like this, guys, do it a couple of times. Any questions on that? So if you have that equation, Van der Waals equation on your reference sheet that you take. Well, on this test, you gotta be at home, right? But still have it somewhere that you can refer to, yeah.
When's the next unit test?
We're gonna finish but the 22nd. We'll finish with this unit.
Then we have the other one, like,
That's the plan. I hope we can do it.
then we have the other one like a couple days before the final, right? The last one.
Yes, it's the day before the final.
That's terrible.
Yeah, it is.
Can we not do that?
I'll tell you what. If you can nail the final, I can make that your whole grade. If you get an A on the final, what does that tell me? You know this stuff.
Can I take the 4th unit test and not take the final?
I like
That's
that.
a better deal.
Yeah, in my 11-10 class, I drop one test and include the final in that dropping one test. But
Can we drop the 4th one?
if we took all of these tests at home, in the testing center, including our unit tests, I could probably say that.
Yeah, actually the ones that are not that bad.
Testing center versus proctored at home. I think it's the title. It's the same.
No, I'll take what we can get, I appreciate that.
But anyway,
We can ace the final. I don't know about
Great as
that,
an
but
bell curve.
thank you.
but yeah.
I think the solution is to just take the final at home.
Unfortunately, I can't do that.
Take the final.
Okay, so that wasn't, it was a little mathy, but if you have the formula, plug and chug, just make sure you're careful. And if you want to, so this is 1.5, and it ideal is 1 ATM. A little bit off, right? So, but it's not a lot off. If you were to do it using the ideal gas law, and you get something way, 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 way different, you might want to check your calculation again, right? I mean, this is quite a bit different, but not like 30 versus 1, right? Or 0.0005 or something. So if you make a big mistake on your calculation, you might be able to catch it, maybe not. Depends on what mistake you make. But so just be careful on that one. All right, should we take a break? Do we have any questions? All right, back in 10 minutes. Here we go. It's getting warm here. All right, so got rid of a little bit, right? So 30 plus 1, 30 joules plus 1 ATM liter. I'm going to do something just real quick, guys. Okay. So 30 joules plus 1 ATM liter. So we know that 1 ATM liter is equal to what? 101.3 joules.
Wait, and in this case, why is P positive?
P is always, well, I don't know that,
Oh, sorry,
right?
yes.
But it's so it's negative P, which is 1 ATM, times change in volume. It got rid of that, so minus 2.5 liters. Change in volume is negative 1 liter, right? So we have a negative turns into a positive. Are we good? Thanks, I kind of went past that quickly. And so that's why it's 30 joules plus 1 ATM liter. But we know 1 ATM liter, in this case, we don't really have to convert. It's already converted, right? Ish. But if it's not, just convert it. And let me show you how to do that. One ATM liter. We got 1 ATM liter per 101.3 joules, right? And that goes away, and we're left with 101.3 joules. You following? So our delta E is equal to 30 joules plus 101.3 joules. And that's going to give us 131.3 joules. So is it exothermic or endothermic? Endothermic because it's positive. Are we good there? So make sure we're dealing with units, and if they're not the same unit, we can't add them. That's like adding x's and y's, right? You got to convert it, make sure it's the same unit. How are you feeling on that? Would you like one more? I'm seeing no. Anybody want one? Okay, let's do one. Okay, so for the next example, again, we want to calculate change in energy when we have a release of 50.0 joules of heat, expanding the piston from 1.2 liters to 2 liters at a constant pressure of 1.20 ATM. Okay, so what do? Write down the equation. Great first step. Equals Q, what's the equation? P delta V. So we know what our P is. Now we got to calculate delta V. How do we do that? What minus what? 2, this is our final, minus the initial. Equals 0.8. 1 decimal place, that's it. Liters. So delta E, what's our Q value? Positive 50 or negative 50? Negative 50 joules. Minus our P is 1.2 ATM. Times our delta V is 0.8 liters.
Convert that
We can, definitely. So negative 1.2 times 0.8 is a negative what? .96? 0.96 ATM liters. And we can convert it. 1 ATM liter has a value of how many joules? 101.3 joules. ATM liters goes away. So what's 101.3 times 0.96?
97.248.
So negative 97.248, right? And we're going to add that to a negative 50, which is equal to what? Negative 147.25, 3 sig figs, joules. We good? Am I going too fast? Making sense of everything?
How did you get the 0.96?
Okay, 1.2 multiplied 0.8. Did I do my math wrong?
Oh, sorry,
No, it's okay.
I just did 12 times 8 and then did some,
I just
okay. No, you're good. Always check. Always, always, always. Even check yourself. Especially check yourself. Well, I'm saying that because it's your grade, you want better, right? Okay? And how many times, oh, I knew that, I just did that stupid thing, right? That's not cool. Any questions? Okay, last idea for today. And then we're caught up. Woohoo! But if you're burned out, it kind of ties into what we're doing next time, so you tell me. Ready for some more? Or? I'm seeing yes, 1 and no 1. It's your guys' time here, yeah.
If we don't get caught up this time, how does it affect catching up in time for the next?
Great question. Great question. This is my first time going through this course, teaching it anyway, and I don't know how long it takes. So far, I've been on top of things until this last little bit, but so it really isn't that difficult, this stuff. So who wants to keep going? Who wants to go home?
Can I have both?
Okay. we're going to keep going. Good call. All right. But at the same time, if we're all burned out, then keep going. We might not get anything out of it, is what I'm saying. Okay? All right. So the next part is heat capacity. What does that sound like?
The total amount of heat that something can take on.
That's right. How much heat can it hold, right?
Like a battery?
Not a battery. Battery's electricity, maybe. Well, batteries, I guess, could take heat too. But so we could deal with a battery, but the heat capacity of an object is the amount of heat absorbed or released when an object undergoes a change in temperature of 1 degree Celsius. So it doesn't matter. I guess kind of it does. So in other words, how much heat can it take in before it changes 1 degree Celsius? Good? So an object can hold a lot of heat. The temperature is just going to go up and up and up and up, right? So how much heat can an object hold until it changes 1 degree Celsius? Can we say it also changes 1 Kelvin? Can we use degrees Celsius here? Can we use 1 Kelvin here interchangeably?
Not 1 Kelvin, 273.
Let's see. If we have 300 Kelvin and it goes up to 301 Kelvin, what's the change in temperature? 1 Kelvin. If we change this, this is going to be 27 degrees Celsius, and we go up 28 degrees Celsius, delta T is also 1 degree Celsius. Do you see how you can use either one for a change in? Because the increments are the same. That's why we can. But for our purposes, we don't have a thermometer that measures in Kelvin, so we're going to use degrees Celsius. Okay? So the equation for heat capacity is a capital C is equal to the amount of heat divided by the change in temperature. So this is capital heat, capital C.
Is that Q?
Yes, that's a Q. Q over delta T. Thank you. Okay. And then we have one that's similar to that, and that is the specific heat capacity. And this is the quantity of heat absorbed or released when 1 gram of substance experiences a change in temperature of 1 degree Celsius. It's specific to the amount of mass. Okay? So the amount of heat absorbed or released when 1 gram of substance undergoes a change in temperature of 1 degree Celsius. Does that make sense, the difference between the two? One of them is an object. Doesn't matter how big or how small the object is. How much that entire object, how much heat it can hold before it changes the temperature of that object by 1 degree Celsius. And specific heat capacity is changing 1 gram of that substance. If we're talking about iron, 1 gram of iron by 1 degree Celsius. So the equation here is lowercase c is equal to Q over mass times delta T. Just a slight difference. One has mass, the other doesn't. If we're looking for Q, we can solve for Q, and we get mc delta T, the MCAT. It's not really the MCAT, but it kind of looks like it. Okay. Anybody here going into medical? Is that the medical test?
Yep.
Okay.
Med school entrance exam.
Yeah. So that one's common if we're looking for the amount of heat. This one if we're calculating the specific heat capacity for a certain substance. Good? All right, almost there. Can we finish? So that's just a couple equations, couple formulas that we can use. And are you given these? You are given both of those. Well, kind of. The heat capacity is in another formula. Well, yeah, it's there. Kind of-ish. All right, let me pull up. Any questions on this? Okay, let me pull up a picture, because remember what happens last time I drew a picture, right? Okay, we'll just keep it G-rated here. All right. So which one has a greater heat capacity, the small pan or the big pan? Larger pan. The heat capacity of the larger pan is greater than the heat capacity of the smaller pan. Does that make sense in everybody's mind?
A little small on both.
What?
A little small on both.
Oh, darn kid. Okay. Does that make sense to everybody? All right. No questions on that? So the amount of so this one can obviously hold more heat before it changes temperature because it's bigger. There's more of it. Okay? But the specific heat capacity, what do you think?
The bigger the mass, the smaller the.
Let's see. C of the small, this is the lowercase c, versus the C of the large. Which one's bigger, or are they the same?
Would they be equal? Because
Why?
you just consider 1 gram?
Yeah, 1 gram of substance. Are they made of the same substance? Yeah, they're both cast iron. So yeah, they're equal. The specific heat capacity of a substance is the same. Doesn't matter what object is made out of that substance, right? So this one is more intensive. This is extensive, kind of ish, right? Depends on, so extensive depends on how much you have. This is intensive. Does not depend on how much you have. Does that make sense? What?
Oh, just another one say. Yeah.
Oh, now you're hungry for some eggs or something? Oh, sorry. Okay.
So we're not looking at the mass like of this one itself, of the like I don't know what's that called.
Well,
Looking for the mass of the like of what it's made of.
should we put numbers to it? Would that help? Okay. So the specific heat capacity of the small guy is still going to be Q over M delta T, right? So the amount of heat, for example, let's say it's 18,150 joules, or 18.15 kilojoules, has a mass of 808 grams, and a change in temperature, let's say we change the temperature of this cast iron pan by 50 degrees Celsius. Good? And we get a value of 0.449 joules per gram degree Celsius. We good? Now if we take that big pan and also change it by 50 degrees Celsius, so the large pan, still going to be Q over M delta T, but it can, if we change the temperature of the big pan by 50 degrees Celsius, would we have more heat or less heat or the same heat?
Let's see.
Well, let's see. We just talked about this right here. What's the heat capacity of the two pans? We're changing both of them by the same number of degrees Celsius. So this big pan is going to have more heat because there's more of it. Make sense? So it's going to be like 90700 joules, a lot more heat, but it weighs more. or it has more mass. Change in temperature is still 50 degrees, and so it's going to be 0.449 joules gram degree Celsius. Yeah? Has more heat capacity, but you're dividing by a bigger mass, so it turns out to be the same. We good? What if we change the temperature change? Would it change it? No, but if you changed it by a bigger temperature, your heat would be more too, right? This would be more, this would be more. Nothing happens. It's going to be the same value. Question, Yazan.
I was gonna ask, like, are we gonna, like, are you finding the heat capacity first and then the specific heat capacity, or like because
They're different.
they're different?
Yep.
For this one, we're finding the specific heat capacity, not the heat capacity.
Yeah, this one's the specific heat capacity. But if we change it by 50 degrees, they're going to have a different heat capacity, right? Or different amount of heat gained. Make sense? Okay, that's 430. We didn't go over an example using this. Should we just do that next time?
Yeah.
Okay, so the worksheet has examples for you. You can try them. I didn't post the answers yet, but I have them done. I just finished just this morning, but any other questions? Okay, have a great day. Thank you.